interference of waves. Now, when two waves interact, they obey something called the superposition principle, okay? Unlike solid objects, they don't bounce off one another. As two waves interact, we simply take the displacement of each wave, or how much we are deviating from equilibrium, and just add the displacements together. So for instance, let's say we have waves on a string. I have this wave right here. Oops, not what I wanted. Always switch tools on me. Okay, I've got this green wave right here. And I'm going to add it to this red wave right here. It didn't change colors. There we go. All right. When the two interact, the superposition principle says the displacement of both we add together. Okay. So when I add the two together, okay, peak lines up with the peak, so we get a bigger peak. The valley lines up with the valley, so we get a bigger valley. There's a valley, there's a peak, and we get a bigger wave. This is what we call constructive interference. When the two waves are in phase, okay, meaning that a peak lines up with a peak, the valley lines up with the valley, and they're roughly the same frequency, all right, we're going to get a larger wave. All right, makes sense. Two waves just combine to make an even larger oscillation. However, the superposition principle also allows for the case where a positive peak can line up with a negative valley. In that case, we get something unexpected. Okay, so here's constructive interference. We get a bigger wave. If we have a positive peak lining up with a negative valley, if they're equal and opposite in amplitude, both waves disappear. That's the superposition principle. And what's interesting here is this is exactly what happens with noise canceling headphones. Okay? In noise canceling headphones, there's a microphone on the exterior of the headphones, and they record what the wave is coming from the outside. They'll digitally invert the wave to create an exact copy of it, but instead of putting a peak where a peak was, they'll put a valley there. And by adding the two waves together, you don't get perfect cancellation, okay? Because we can't perfectly cancel the wave from all directions. We need an infinite number of microphones and an infinite number of speakers to do so. But we can get a pretty good approximation and destructively interfere with the wave coming in and effectively cancel it out. Begs the question, where's the energy going? Well, one way of thinking about where the energy is going is instead of the energy going in the ear, the energy ends up propagating away from the headphones. But again, here can be the input. Here is what the headphones can generate. And the result is noise cancellation. And again, you can see two pulses on a string passing by one another. Here's a larger pulse, here's a smaller pulse. They combine to produce a smaller pulse, but they don't cancel each other out forever. The smaller pulse ends up going on its way, the larger pulse ends up going on its way. Okay? They act like ghosts. Okay? They don't interact. Waves on a string, if the end is fixed, you get what we call a phase shift. Okay? Here's the wave coming in. Okay? Here we have this positive peak. Positive peak comes in. If this is fixed right here, that changes a phase by 180 degrees. Now the peak has become a valley. Okay? The reflected pulse goes this way. This is going to be important for standing waves, because with standing waves, one wave comes in and the other wave bounces off the fixed end and interferes with the incoming wave. All right? Because they're 180 degrees out of phase, this will lead to some very interesting patterns. If the end of the string is not fixed, you get no phase change. All right, so what is a standing wave? Well, standing wave is probably a misnomer. It's not really just standing there. We get standing waves when we have one wave traveling in one direction, let's say in the positive x direction, and then we have that wave reflecting off of something, producing a new wave traveling in the negative x direction that is going to combine with it by the superposition principle. Now, unless you have the exact right frequency, okay, this first wave, okay, let's call this wave 1, the incoming wave, and the second wave, wave 2, the reflected wave, these two waves are going to destructively interfere and basically cancel each other out. There are waves at just the right wavelength, okay, just the right wavelength for a standing wave, okay, that produce these standing waves, because instead of destructive interference, we get constructive interference. Okay, it's a little bit complex to analyze why certain waves get constructive interference, why certain waves get destructive interference, but it really has to do with the distance between which the wave is tracked. Now, again, to get a standing wave, we need two ends, one end down here, one end down here, and each end sort of acts as a reflector. If the wave fits such that there's some half wavelength relationship with the length of the string, okay, you will get a standing wave. All right. Now, standing waves basically, okay, have points where we get no oscillations. We call these nodes. All right. This is where you get complete destructive interference, and those positions of the strings will never move. Other points, called antinodes, are places on the standing wave where the amount of displacement is maximum. Okay. So once again, let's say I have a little oscillator right here, causing the string to vibrate up and down. All right. I need to have it vibrate at just the right frequency so that my wavelength is some set up such that 1/2 the wavelength is some integer value of that length. Okay. All right. Now, the lowest frequency I can have is what's called the fundamental. Okay. In this particular case, I've bound the wave between this end and this end. Maybe one end has an oscillator, one end is simply tied to something fixed. Okay. The actual wave itself for the fundamental, okay, is twice as long as the actual length of the string. I didn't do a very good job drawing that, but basically the full wavelength here, the wavelength, okay, is equal to twice the length of the string. Okay, that produces my lowest frequency, or my fundamental. Now, if I cut the wavelength in half by doubling the frequency, now my wavelength is equal to the length of the string. okay? Triple the frequency. And now my wavelength, again, is some relationship. In this case, it is 2/3 of the length of the string, okay? So generally, here is what different standing waves would look like. Again, imagine that this end and this end are bound, okay? We call this first one the n equals 1 mode. Notice it has one anti-node, okay? Just one place in the center where it oscillates up and down. That's one anti-node, okay? If I cut that wavelength in half, I'm doubling the frequency. I've got my ends here. I've got a node in the center. And notice that this n equals 2 is vibrating at twice the frequency as the n equals 1. Okay, now I go to 3 times the frequency of the fundamental. I get a node here. I get a node here. Now I have 3 antinodes. Okay, 3 antinodes. One here, one here, one here. So the mode number tells you how many antinodes there are there, or the number of antinodes tell you what mode number you are. Again, we can do this for n equals 4 antinodes, n equals 5 antinodes. And in each case, the wavelength of my standing wave is twice the length of the string divided by some integer n, where n equals 1, 2, 3, 4, and so on. Okay, those are standing waves. This is a nice illustration because clearly we can see this frequency is really, really low. Okay, this frequency is twice as high. This frequency is 4 times as high. Okay, and another look at the fundamental. Okay, again, this is our lowest frequency that we can have oscillating. All right, double the frequency, and you get n equals 2. Triple the frequency, you get n equals 3. Okay, again, think about this. The velocity is fixed, so wavelength over frequency. If I am cutting this value in half, to keep the velocity fixed, this has to double. This is an actual picture showing a fundamental frequency. You got a little oscillator right here, which is moving up and down. And, you know, clearly you can see, here's my big antinode. There are no nodes in the center. We say that technically where it's not moving is a node. So I guess at both ends, you would have a node. We normally ignore those. Okay, so that's a fundamental. That's the lowest frequency. And this length right here, that is equal to 1/2 the wavelength. At twice that frequency, okay, oscillating up and down, not perfect here, okay, but you get a node here. Some of the problems here is, yeah, this is fixed right here, but to get the vibrations, you don't have a perfect node at the end. So where the oscillator is, we don't get perfect standing waves. Here's n equals 3, so you see a node here, node here. Okay. So again, there's your n equals 3. And if we look at the wavelength, one wavelength is from here to here. Okay, and if we follow this, here is one up. There's your peak, there's your trough. So that's one complete wavelength. And as we said before, the wavelength is equal to twice the length of the rope divided by n, in this case, 2L over 3, 2/3 the length. Okay? And just going back to the previous one, the n equals 2 perfectly fits along the length. Here, the wavelength equals 2L divided by 2. That was our n right there. So it's just equal to L. Okay, standing wave on a string. We've talked about the wavelength. We've said that the wavelength has to be equal to twice the length divided by n, where n is the node number. Okay, what about the frequency? Well, we can write the frequency in terms of the fundamental, or the first harmonic. Sometimes it's written as F0, sometimes it's written as F1. All right. Now, we know that the velocity is equal to the square root of the tension divided by the mass per unit length. Okay. So for our first frequency, or fundamental frequency, that will be equal to the velocity, okay, divided by the wavelength. Now, the wavelength for the fundamental is 2L, okay? So if I substitute in here, I get 1 over 2L times the square root of the tension divided by the mass per unit length is equal to my fundamental frequency. Okay? If I want to change the wavelength is 2L divided by n. All right? For each subsequent standing wave, get f of n. We put n in here, we put n in here, and that is that equation right here. So it shows that once you know the fundamental, each harmonic is some integer value from the fundamental, okay? N equals 2 is twice the frequency. N equals 3 is 3 times the frequency. N equals 4 is 4 times the frequency, so on and so forth. Okay? Find the first 4 harmonics of a 1 meter long string with a mass per unit length of 2 times 10 to the minus 3 kilograms per meter under a tension of 80 newtons. So once again, we're going to use this equation right here, and we're going to find the velocity, which is equal to the tension divided by the mass per unit length. Okay? So 80 divided by 2.0 times 10 to the minus 3 is going to give me 40 times 10 to the minus, 40 times 10 to the third, which is basically 4 times 10 to the fourth. Take the square root of that, and we get a nice number, 200 meters per second. Okay, so what is the fundamental? Fundamental is equal to, fundamental frequency is equal to the velocity divided by the wavelength. Okay, so 200 meters per second divided by 2 times the length, 1 meter. Well, that's easy. The first harmonic is 100 hertz. Okay, if I calculate all the other ones, all I need to do is multiply n to this. So what are the first 4 harmonics? Well, when we're dealing with the fundamental, it's n equals 1, it's 100. When we're dealing with n equals 2, it's 200, n equals 3 is 300, n equals 4 is 400. I could go to the 22nd harmonic. It would be 22 times 1,000, or 2,200 hertz. Okay? So that's how the standing waves work. Okay? As we go to a higher n number, the frequency goes up. Frequency gets larger and larger. Okay? As you go to a higher and higher n number, the wavelength gets smaller, because as it vibrates faster and faster, you have more nodes and antinodes, so the distances between them get smaller and smaller.